Hello, and thank you for joining us in getting a better understanding of exceptions and reflection with C#. Now let's understand exception handling. .NET has the try, catch, and finally keywords to help handle exception. In C#, there is an exception class that is thrown, and that the CLR supports and looks for a catch by walking the up to the caller. If a catch is found, the execution continues from there, else the program halts. Exceptions are a way to help identify errors in an application. To make an application resilient, you should write code that can predict an error and handle it. There are 3 parts to handling exceptions. We try a scope of code, and if an exception happens, we catch it, and finally, we execute another scope. If we don't handle exceptions, the program stops where the exception happened. You have seen how to generate an exception, but not how to handle it. Let's see this in action and then explain as we go along. Let's try and open a file that does not exist. We get a file not found exception. Most of the .NET BCLs have documentation to let us know if a method is throwing an exception and what kind of exception it is. We can also gather more information about the exception. We can get a general message about what the exception is as well as the stack trace. The stack trace is the code path that generated the error. The first line of the stack trace shows where the exception generated. Each line before it is the path it took to the calling code throwing the exception. As we mentioned, this is also the path that the CLR will take to find a catch declaration. If found, it continues from there. What if we have the file but have an issue with the path? In this case, our exception didn't work. The reason is that we are only catching the exception of file not found. We should be catching directory not found. What if we call a library that we don't know what kind of exception we might get? In this case, we can just catch the exception. This is a catch-all. We have seen code like this as well. Don't write this type of exception handling. If you encounter this type of code, rewrite it to either log or output the error somewhere. When we run code like this, we get an exception, but we don't do anything with it and it becomes hidden. This type of error is extremely difficult to identify unless you walk the code one line at a time. There is, however, a debugging technique that can help us. We will show you, but we will have a more thorough review of debugging with Visual Studio. In Visual Studio, go to the Debug menu next, select Windows, then select Exception Setting. Now check the top level checkbox for Common Language Runtime Exceptions. And if we run the code again, we can see that even though we had a catch, we break on the code throwing the exception. This can become annoying if your code is throwing a lot of errors, which brings us to our next point. Your code should not be throwing too many errors as it can slow down your application. The try catch and finally is not an issue. It's the exceptions being thrown that produce performance degradation. But remember that the CLR walks the stack, and that is what will slow down your app. You can nest exceptions. For example, take an application that displays some data to the end user. The application also catches all exceptions and displays a message when an exception is encountered. This application also makes calls to a database if, let's say, a table is not found. This can happen when a deployment doesn't go well. When the database throws an exception, it is now being caught, and the exception message and stack trace may be visible to the user. You should never know the underlying exceptions to the end user. Always catch exceptions and wrap them. The exception class has an inner exception that we can use. You should always log and wrap your exceptions. Now you know the best practices for exceptions. Microsoft has really great documentation on that here, and here it is. And we will link it in our description selection. You can always create your own exception types as well as inheriting from the exception class and extending them to have additional information. We will create one that has the method name. Also, note that we can have a mix of a catch-all exception with our custom exception, but our custom exception must be before the catch-all. When rethrowing an error, please make sure just to throw it. Let's take a look at why. If we catch the exception and throw back the exception, we lose the stack trace location of where the exception occurred. Now, if we modify our code and just throw it, we will have the stack trace. Let's talk about the finally. When we try a scope of code, then catch the exception, the finally is responsible for executing no matter what. We can also just have a try and finally no catch. The exception is still thrown, but we get to execute the finally section. For now, this should be good enough for the beginner to intermediate level. This concludes our exceptions section, so let's talk about reflection. Now, what is reflection? In the .NET world, reflection is the ability of an application to examine or describe assemblies, modules, types, at runtime. You already know types. These are classes, interfaces, structs, and enumeration and other types. So let's identify modules and assemblies. In the real world, you would create DLLs that can be shared or use someone else's DLL to augment your application. When you deploy, then you would package the XE and any other DLL. So from the perspective of deployment, all of your supporting DLLs and your XE is an assembly. The XE and the DLL are modules. The modules then contain types. Now, how do we examine these structures? .NET has a BCL system.reflection.dll that allows us to do that. Now, we are going to create a simple console app that depends on a DLL. We then will use reflection to look at the details of what was discussed. We can use the assembly class to load our XE or DLL. Since our XE in Windows is just pointing to our DLL, we will load the DLL. Now we can look at the modules. Notice that we only have one DLL. So what happened to the reference DLL? We can use a method from the assembly class that will get us the reference assemblies. So now that we have the module, we can walk and look at the types, then the type methods, properties, and fields. Now we can see some methods, but not in our program class. We are missing the main method. By default, you will only get the public instances of methods, properties, and fields. To get the main method, since it's private, we would need to use an overloaded method and passing a binding that is for the private modifier. Now that we passed a non-public binding, nothing happens. That's because we also need to tell it that main is static. Now we see our main, but all the other methods are gone. Since we are using the overloaded method, it only gets what we ask. So we would have to pass additional binding to get to them. What were the other methods? Remember when we went over classes, we stated that all classes inherit from a root level object. The other methods came from that root level object. So if we use dnspy and look into our app, we can see that object does have the methods that we were displayed. One other thing to note, the methods displayed seems like it was a little less than what is showing in the dnspy. And look into our app, we can see that object does have the methods that we were displayed. One other thing to note, the methods displayed seems like it was a little less than what is showing. That's because most of the methods are overloaded, meaning that they are the same name but have a different signature. In get methods call, it's just getting the names of the methods and returning distinct. How does reflection help us? If you are working on a large project and need to analyze migration or how your changes would impact the project, you can use reflection. Reflection can also execute code. Why would you ever do this? If you want to build a modular system, then you can expose an interface and have other supporting DLLs inherit your interface, and you can then load them at runtime and call the methods you need. So let's see this in a working example. We will create an external interface project that will hold our interface. Then, two other projects will inherit our interface. Both projects will output to the console, but we are going to get fancy and color code our console. One project will output red and the other one green. Then, in our main application, we will load the assemblies, and based on our message, we will call the appropriate DLL and call its output to display our message with color coding. Now you're wondering, can we not just reference the projects? Yes, you could if the colors would not change, and you would have to modify your main application. What if tomorrow it's not red but burgundy or has a different background? I hope that you can see now that you wouldn't want to modify your main app. So let's create our external interface, and it will have one contract for displaying a message. Next, we will create our other projects and implement the interface and add our color coding to the message. One thing to note, that when dealing with the color coding of the console text, you must set the color before writing to the console. If you want to change the console color, you must do so before writing the next line to the console. And it's best to remember the previous console color, then reset it back to the original color after completing outputting the message to the console. Note that you can also reset color method, but if the previous code had modified it, we would be reverting it and may have an undesired effect. Okay, now we will create a folder called plugin. This is where we will copy our color extension DLLs. Next, we will use assembly load context class by inheriting from it. We will create a plugin load context class that will be responsible for loading our assemblies in memory. Next, we create a constructor for our class to load our assemblies. Then we will use another class, assembly dependency resolver. This class will help us if our assemblies depend on other assemblies. It will, as the name suggests, resolving the dependencies. Next, we override two methods from the inherited class assembly load context to do the heavy lifting and loading of our assemblies. Now we are ready to load our plugin. Let's create a method that we will use our plugin context to load the plugins from our folder. We are going to use directory info and file info classes to help us get the DLLs. First, we get the path of the plugin and then create a directory info object so that we can iterate through the folder and get all the DLLs. Then use our load context class to load the assemblies. Now that we have our assemblies loaded, we need to get the output commands so that we can execute them. We will create a new method and pass an assembly into our method. We will then iterate through its types until we find a type that is inheriting from our interface. Then we create our interface object so that we can use it. Now that we have our plugin output, we can use the right message to print to the screen. Please note, we could have done this without an interface, and if we did that, we would need to know what method to call. The interface binds a contract that a plugin must support. This was a pretty simple demo. Let's see how we can use reflection with our previous SuperDuper University application. And in our SuperDuper University application, we read data from files for students and instructors and map them manually. We want to create a single mapping method that would map an object regardless of whether it was a student or an instructor. So let's understand the problem in more detail. We will read any type of class or struct and get all the public instance properties, then map that to the column to what we would need the column headers, and we match the header value to the property name. If the names match, we use the column value and set it to the property. We need 3 pieces of data: column names, properties we are working on, and column values. We can get the column names from our file. In our loop, we start with line index 1, as line index 0 is the header values. Then we would split it so that we have our headers and column values in an array. Next, we create a method that passes the 3 values we need, noting previously. Now we iterate through our column headers and use reflection to get the properties of the object we want to map. Next, we start to set the value if the column name and property name match. You have to be very specific in what you want to return. Okay, so now that we get our property, let's set its value. We can use an internal method to help us with that. We could add logic if the property type is int or date to do the conversion, but that would require us to change if we get a type we hadn't accounted. We can use the convert class and use the change type method. We pass or column value and the type it should be converted. Now before doing this, the conversion method may throw an exception if the object is null. We need to make sure that we only set values to our object if it's not null. Anyways, check for nulls and be defensive coder. We could have caught the exception, but we do not need to do that if we just check for nulls. Next, we need to call the setValue method, passing our object if we want to set the value. Now that we have set the values of all the properties, we can return the object. Now, one thing to note is in our method, we converted our student and the instructor structs into objects. If we didn't, we would not be able to set any values to it. If they were classes, then it would have worked. Since we are dealing with structs, the value is being boxed. If you don't use objects, we will lose the value. If you do a quick search on reflection and setting struct values, you will find more detailed information as to why that is. This concludes this video, and we can thank you for all your support. In the next few tutorials, we will go over how to work with drives, directories, and files, including images. So be safe, and we look forward to our next tutorial.